Let me give you a hint. ULSI would not have happened if we did not know how to control lateral profile. Now tell me why lateral profile is important.
Sir, as we scale down the device, sir, the gate and the drain and source are coming closer as we scale the device. So, sir, we have to have a better control over the fabrication of drain and the source so that they don't actually come so close that
you said it.
They overlap.
You said it. And what does that do?
Sorting the channel.
Yeah, remember what we told you? The short channel effects? Remember how thresholds get kaput if you don't control the short channel effects? This is threshold, this is channel, effective channel length. You want, ideally you want this. If your design says, I will make a device ideally, then no matter what this span of channel length variation is in the devices, then the threshold is stable. But why? Because the threshold is what determines the performance, the current, right? Threshold of the device, when it turns on, that determines whether the transistor is on or off. And how much current is transported through that is a function of what? Gate voltage, right? Characteristic of transistor. Go look at the characteristics. Two important characteristics. The drain current versus gate voltage. Drain current versus gate voltage. Right. So, those are the two very important characteristics. And go to the basic equations, what the threshold means, and what the IDS means. Remember, I think I showed you earlier in the lectures. So please go through that. Please be familiar intimately with that. Very intimately with that. Because that is the crux of device design. Okay? So, what is in reality? In reality, any technology does this. What does that tell you? Any generation of technology has this threshold versus unaffected. Why? Because the type of device we built is a surface device that two things. This is short channel and the threshold modulation by dB. Those two phenomena, you should really understand that hard. Short channel effect and dB. Drain-induced barrier load. Okay. They move up, they make this effective in the range that, and the design technology is done, how nicely you can do this kind of thing. In other words, a superior technology would be this, an inferior technology would be this. That's how important the short channel effect is. How you control the short channel effect is the most important parameter in scaling the devices. So please be intimately familiar with that and recognize that you as a device designer is rated by how well you put the process together to improve short channel effects. However, I'll talk to you in a special lecture. The reason you run into the short channel effects is because you're making the device linear in the channel on the surface. If on the other hand, you have a fully coupled gate, to gate to channel, a fully coupled gate to channel, an ideal device. Here is source or drain, or they can be drain or source, doesn't matter. And here is the gate. This is looking down. The gate is coupling between the source and the channel. In a complete, it's no longer planar coupling. There is no short channel. Right. So an ideal device has to be shaped like that. And I'll talk to you on a special lecture how the future memories will be built on nanowires, where the field of transistors will have source and drain around you, okay, in the 3D geometry, so there is no short. Okay, that's a separate topic. We'll talk about that. Remind me. So, when we look at scaling, the first thing we look at is the device point. How can we contain short channel? And you know FinFET, right? Some of you are familiar with FinFET. It only goes a certain way and not goes enough. That's why the ideal device is this, and there's the future device for 5 micron, 5 nanometer technology. And successful implementation of nanowire feedback transistors, in my opinion, will at least extend silicon technology for at least 1, possibly 2 decades. Beyond what they, even if we cannot reduce the feature size less than 5 nanometers. Okay? So I believe you still have a very long future. I may not see it, but you would see it. And you would participate. You would participate in those kind of transistors, which will have some talk, it's one of the special things. Because I espouse an awful lot of non-volatile memories based on that kind of technology. Hasn't built yet, but someday they will be built, and you will remember me, and I'll look up from the sky and say, aha, I told them ahead of time. Right? So, good luck to you. So as you know, in device design we employ impurities with high solubility in solution. Boron, phosphorus. Why boron is an acceptor? Why phosphorus is a donor? Antimony. What is this? Atomic number. What's atomic number? What's atomic number?
Number of proton.
Number of like 6.
Diffusion.
Precisely.
Number of proton in an
Yeah. Number of units of charged nucleus. Yes. Atomic number. Very good. So we have boron
5.
with 5. Phosphorus with 15. Arsenic with 33. Can anyone tell me what's the antimony? How many protons inside an antimony atom? Can anybody guess? Yes.
50 is 50.
Huh?
55.
Very close. 51. You said it right. 51. That's right. So as you can see, if the atomic number goes up, so the atoms are heavier, right? And the more the atoms are heavier, what happens?
The device will be heavy.
Have you looked at the Olympians who make very fast moves?
Athletes.
They are not heavy, are they? That's the secret. Don't be heavy. You want to move fast, don't be heavy. All right. So, what makes these borons phosphorus? Boron is an acceptor, and phosphorus is a donor. All right. What does the acceptor means?
You can accept an electron from the element.
Precisely. And the donor, I want to give away an electron, right? So I'm ready to give away an electron. It's creating suffering in me, I give you up. So that's how what donor and acceptor is the characteristic of the nuclei, the external electrons, their energy states of electrons, while either they want to have an electron and create a more stable structure, or they want to give up to create a more stable structure. One or other, they have to be more stable. So that's what makes the difference. All right. Diffusion. As I mentioned to you earlier, that often they create an intimacy between the defects. The atoms and the defects kind of like each other. So they get tangled up, and it either facilitates movement, the defect says, go, 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 I'll push you, okay? Or they say, no, I'm going to hold you. So there are two types. We've seen that in our life, right? In our relationships. So it's like that. So, anything that's vacancy driven, what's vacancy? Right, that's a good one. What's vacancy?
Divider of electrons.
No?
Missing of the atoms or letters. Missing of the atoms.
Missing atom, exactly right. The vacancy is where an atom should be in crystal lattice, is not there. And why it isn't there?
Because of impurities.
Remember this morning we talked about
Defects. Defects.
Defects like defects.
Yeah, remember we talked about some very fundamental thermodynamic entropy. Right? It's fundamental to the nature, entropy. So, it's natural to have defects. It's very natural. And so they're thermodynamically stable. Both interstitials and vacancies are thermodynamically stable. They make who we are. Right? So because of that, some of these are vacancy driven, some of these are interstitial driven. So most metallic impurities, the heavier ones, the slow moving ones, have limited solubility. That's no wonder, right? Because they're big and occupy interstitial sites. But also no wonder, right? Because they're big. The only place they can occupy is move the silicon away, and the gold atom like this comes in, and the slim meat has to be pushed out. Okay? And he occupies probably more than 2 atomic sites. This is beginning. That's the way the world works, right? Nature. So these have limited solubility of interstitial sites in local silicon crystal layers. Transport interstitial driven, and the phenomenon is called interstitial diffusion. because they basically displace and push into the crystal lattice themselves and don't necessarily occupy the place where the in crystallographically where the atom should stay, because they're usually too big. Interstitial diffusion is much faster compared to substitutional diffusion. Can you tell me why? Can you tell me why an interstitial diffusion is much faster than substitutional diffusion? Look at the speed, velocity. 1 × 10⁻⁵ centimeters per second versus 1 × 10⁻14 centimeters.
So in substitutional, we have to throw out one atom and then we have to introduce another one.
You have to break some very strong bonds, right? Yeah, you have to break very strong bonds to displace that particular atom in the lattice, right? Well, the interstitial, it just looks for some space, and once it moves in, it squeezes in pretty quickly. Okay? So, why boron is an acceptor and why phosphorus is a donor, you know? You already know, right? It's the